Good afternoon, ladies and gentlemen. It's a pleasure to be here for the first time in presence. My talk is related to an application for the fatigue limit estimation of welded joints using the so-called cyclic error curve analysis. We all know that welded joints are engineering structure quite sensitive to fatigue failures. And in this context, the fatigue limit represents a fundamental parameter to design against fatigue. Frost, in an important work, observed that the fatigue limit is associated with some crack at the notch tip, but this crack has no more the capability to grow. These cracks are arrested. In this context, so it's easy to understand how the fracture mechanics can be a suitable tool to predict the fatigue limit of certain structures. The problem we have to face is that we must deal with short cracks that in general behave differently from long cracks. In particular, they can propagate even a lower stress intensity factor is applied if compared to the one for long cracks. To deal with this problem, we can adopt the so-called cyclic error curve, which take into account the evolution of the fatigue crack propagation threshold as a function of the crack length itself. And not only takes into account an intrinsic component of the threshold related to material properties, but also to closure phenomena. So it describes the evolution of closure phenomena during propagation. The problem is that, or the question is, how can we relate the cyclic error curve, or how can we use the cyclic error curve to predict the fatigue limit of welded structures? The first to answer this question were Tanaka and Akinawa, who, starting from a notcher component, they insert a crack, which have shown to exist by Frost. Then the corresponding resistance curve, so the cyclic error curve, the evolution of the fatigue crack propagation threshold as a function of the crack length. And then the last point of the fracture mechanics triangle, the evolution of the stress intensity factor with the crack length itself. The latter parameter is a function of the external applied low stress. So if we can lower it until we reach a tangency condition between the applied stress intensity factor, the driving force, and the resistance curve. This means that the crack has no more, in this point, the crack has no more force to propagate, no more energy to propagate. And we have defined the fatigue limit as a tangency condition in between the driving and the resistance force. Just to show you, we can have another scenario in which no arrest condition is found, but we can identify an initiation condition dependently on specimen geometry and component geometry. The problem we must face is how to define the initial crack size from which start our investigation, our analysis. One of the most interesting solutions to face this problem is the one proposed by Zerbst and Madia, which consists in using the cyclic error curve analysis proposed by Tanaka and Akinawa in a different manner. We must define the driving force at the fatigue limit and then introduce the resistance curve and move it, sliding it along the crack length axis until we reach or a tangency or an initiation condition. And then we can define, engineeristically, a value of the initial crack size. So the aim of this work was just trying to define experimentally this value of initial crack size for a welded joint. The starting point was the definition of the driving force at the fatigue limit. The fatigue limit of the component has been evaluated experimentally by the Y factor, so the normalized stress intensity factor by means of linear elastic finite element analysis. The considered geometry was a non-occurring fluid welded joint which has been stress relieved to avoid the effect of residual stresses. And the material just a standard S355 G2+N structural steel, so nothing particularly special. From experimental test under constant amplitude, fully reverse axial loading, we evaluate the finite life and the fatigue limit with a modified staircase procedure of the joints considered. And the outcome of this analysis was the fatigue limit of these structures consisting in 236 megapascal. The next step was just the first input to be given to the finite element model, so the evolution of the crack shape as a function of the crack depth. For doing this, for analyzing which is the crack shape to be adopted in the finite element analysis, we performed some new experimental tests by retesting at a slightly higher stress level the run-out specimen from the staircase procedure. We applied a two-block program in order to benchmark the fracture surface and obtain the evolution of the crack shape during the propagation. Then we fitted with a simple semi-elliptical model that obtained a benchmarked crack, and this is the evolution of the relation between the major and the minor axis versus the crack depth itself. Then we input this parameter, this evolution of crack shape, in a finite element model with measured locally well-bead geometry, and we input also the crack size ranging from 5 microns to 200 microns. The finite element model has been realized according to different procedures, so two different techniques. The one is the peak stress method, which is an engineering approach to rapidly estimate the notch stress intensity factor by means of linear elastic finite element analysis having rather close meshes. The next tool was just the fracture tool implemented in ANSYS, which is basically based on the J-integral, linear elastic J-integral calculation. Just to give you an example of the outcome of the results, here I've reported the evolution, the distribution of the stress intensity factor along the crack tip line for two different crack sizes, the smallest one, 5 microns, and the largest one, 200 microns, with highlighted in green the point at the deepest point on the crack surface on the crack tip line, and the point B1 or B2 almost similar for this crack. Then we have taken this value and plotted them against the crack depth itself for having an idea of the evolution of the normalized stress intensity factor during propagation. So having in hand the resistance curve, we moved to the evaluation of the resistance curve, the other point of the fracture mechanics triangle we have defined on the first slide. It has been performed by means of experimental tests made thanks to SE and B specimens made of base metal, the same material of the welded joints, and one with K-groove full penetration welded joints made in order to investigate the effect of the resistance curve also for the welded material. In the latter specimen, the electrical discharge machine notch has been performed inside the heat affected zone. Then we moved, as suggested by the relevant literature, to a compression pre-cracking procedure using a resonance suction machine and taking advantage of an 8-point bending device for applying also fully reversed loads. Here you can see the specimen with the ADM notch, and in this case we used the DCPD device in a standard configuration but thermally compensated to measure the crack size. Oh, sorry. Well, from compression pre-cracking, we obtain a closure-free crack from which we started to reverse the load, so apply positive loads or at load ratio equal to -1. We measure the crack propagation, crack increment, and the consequent arrest. Each point at the rest condition have been then located in the cyclic arc curve, so we recorded the corresponding fatigue crack propagation threshold and the crack length itself. Then we stepwise increased the load and recorded different points of the cyclic arc curve. Just to have a better description of the higher part of the cyclic arc curve, we switched at a certain point where no more crack arrest has been identified to K-controlled test at delta K constant procedure. The outcome of this test is reported here. In black line, we have the results for the base metal, while in green line, the one for the heat affected zone material, so the welded material. Here we can see that the crack propagated inside the fine-grained heat affected zone of the SE and B specimen. Then the second outcome from this result is that for very short crack propagation, no significant difference has been found in the comparing the base metal and the heat affected zone material. And then we also compared the results we obtained with other from the literature, and we have shown that they are consistent with them. The latter but not the least, I fit the results, the experimental results, to perform then the last step. So the cyclic arc curve analysis aimed at define the initial crack size. So as I showed to you before, we defined the driving force at the fatigue limit. Then we add the resistance curve, and we have slided it against the driving force at the fatigue limit to obtain the initial crack size. The results is this one. So we obtain with this technique an initial crack size to equal to 10 microns to be used in the future for assessing the fatigue limit of welded structures. This is a fitting parameter, let's say an engineering parameter, to be adopted as a material parameter in the cyclical curve analysis, not in the calibration way, but in a design way. So fixing the driving curve and the resistance curve and moving the driving force. Just to highlight that our results is consistent with other proposed and obtained in the literature from different consideration on the choice of this parameter. Just to conclude some remarks, in this presentation I've shown that the cyclical curve can be a useful instrument to evaluate the fatigue limit of welded structures. The problem is that it requires the definition of an initial crack size just to use the linear fracture mechanics calculation. In this work, the initial crack size has been calibrated adopting the cyclical curve analysis in using an hollow carrying fluid welded joints with transverse attachments. The driving force has been evaluated at the fatigue limit, the ladder, investigated thanks to staircase procedure, and the shape factor experiment evaluated thanks to finite element analysis, in which the experimental crack pattern shape has been inputted. Then the resistance curve has been evaluated experimentally, and what I want to highlight is that no significant differences have been found between base metal and fine-grained heat affected zone for very short crack propagation. At last, we obtained, thanks to the cyclical curve analysis, an initial crack size equal to 10 microns, consistent with the other results from the literature. I finish, and thank you for your attention. If you have any question, please ask.
Thank you, Luca.